In this tutorial, we will show an example of how to calculate the total photosynthetically active radiation intercepted by a crop during its cycle using a very simple model that relates the fraction of radiation intercepted by the crop with the crop coefficient. And this is summarize what we are going to do to calculate the fraction of intercepted radiation in this diagram, which shows the values that we are going to assume for this fraction over the crop cycle. And you can see that the time course of this variable, it follows a very similar pattern as the FAO crop coefficient method. During stage A, while the crop is still not covering the soil or covering a small fraction, we will be assuming an average fraction of radiation intercepted by the crop of 10%. Then we have stage B, which corresponds to the stage of rapid growth of the crop until it covers, let's say, 80–90% of the soil, or it is approaching its maximum cover. During stage C, it's the stage with the maximum crop coefficient usually, and we will assume a maximum value for the fraction of radiation intercepted by the crop equal to the crop coefficient minus 0.03. In stage D, we will also follow the same approach. We will be calculating the fraction of intercepted radiation as the value of the crop coefficient minus 0.3. This decay in the fraction of intercepted radiation is very coherent with the fact that when senescence starts, the leaves die or age, so they are not contributing to photosynthesis anymore. And that's the reason why this model should consider a decay in stage D, despite the crop may cover the full, the 100% of the soil. Okay, well, for calculating the values of the fraction of intercepted radiation in each day in the cycle, we just need to know the values of the maximum crop coefficient and the value of the final crop coefficient for a given crop, as well as the durations of the different stages. Once we have built this function, once we have the values for every single day, we will calculate the intercepted PAR. PAR stands for photosynthetically active radiation, as the product of 0.45 times the fraction of intercepted radiation times solar radiation, where 0.45 represents the ratio of PAR over total solar radiation. Well, we are going to do an example for rapeseed, in which we have collected the values of the maximum crop and the final crop coefficients for this crop from the tables and appendixes in the book, in this case from table 10.1. The value of the maximum crop coefficient is 1.15 and the final crop coefficient is 0.35. In the left-hand side, we have a big table which contains the date, the day of the year, and the solar radiation recorded in every day during the crop cycle, which starts in the 1st of December of the year 2018 and finishes on the 21st of May of the following year. Then in column D, we have we have assigned the stage that corresponds to every single day during the cycle. Stage A takes 35 days, stage B 40, so 35, 40 in this example. For stage C, we have 63, and finally 34 for D. Okay, let's make the calculations. Okay, during every single day in stage A, we will be assuming a value for the fraction of intercepted PAR of 0.1. So we will write 0.1, and we will adopt this value in every single day in this stage. In stage C, the value will be the maximum coefficient, which is 1.15 minus 0.3, which is 0.85. So we go to stage C, and we will write 0.85 in every day in that stage. Finally, in stages B and D, we will have to interpolate linearly, because the fraction of intercepted radiation will be either increasing or decreasing as the time goes by in the stage. In the case of stage B, it takes 40 days. We start from 0.1, and in each of the days of the stage, we will add the following 0.85 minus 0.1 divided by the number of days, which is 40. This is the amount or the units of the fraction of intercepted PAR that we increase in a day in stage B. Well, this should be multiplied by the number of days in stage B. At the end of the first day, we will have 1 day, and we are going to use this command for trying to reuse the formula in the whole stage. If calculations are right, we will finish the last day of stage B with a value which is exactly equal to 0.85, the value of stage C. The same goes with stage D. In this case, we have to interpolate between 0.85 and 0.05. Here we start from 0.85, and each day we will be reducing this amount by 0.85 minus 0.05 divided by the number of days in stage C, which is 34. And if we want the value at the end of each day, we just can use the same approach to expand the formula down, so that if things are done properly, we will finish in 0.05, the target value. You can also check that everything went fine by plotting the time course of the fraction of intercepted radiation. If it has this pattern, it will look fine. Well, now that we have the fraction of intercepted radiation, we can calculate the total intercepted radiation by the crop in every day in the cycle. We will have to multiply the fraction of PAR over solar radiation, which is here, and this times the fraction of the radiation that is being intercepted by the crop. This will lead us to a pattern that is similar, but that has some points below the envelope because of the presence of cloudy days, of course. Well, also, now that we have calculated the radiation that is intercepted, the PAR that is intercepted by the crop in every single day in the cycle, if we sum all the values, we will get the total intercepted PIR, which in this case will be 706 megajoules of PIR per square meter.